We are moving on from chapter 10 today. I'll just mention, in case you didn't notice, in chapter 10, though we could have done addition reactions to alkynes, we didn't. We used alkynes in synthesis. We learned how to make carbon-carbon bonds. We did not do halogenation or hydrohalogenation or hydration of an alkyne. You can do all of that. The principles are basically the same as they are for alkenes. Consequences are a little bit different because you got two double bonds to work with instead of one. And frankly, the reactions are kind of tricky and the mechanisms are not as simple as is presented in the text, so we're just sort of going to ignore that. The study guide in chapter 10 doesn't have you do anything with addition reactions to alkynes, but just in case you've been hearing some things or overachieving and reading more than the study guide tells you to, that's why we're not talking about it. All right, we're going to talk today about oxidation and reduction reactions, and this means something a little bit different, or rather it's a different application of the principle that you would have learned in I'm just noticing that the screen is not displaying stuff. I'm wondering how long you were going to let me. I wasn't drawing anything yet, at least. See? There we go. Oxidation reduction has a little bit of a different application in OChem than it did in Gen Chem. We're not going to be balancing half reactions or worrying about electrons as products of various oxidation reactions. For us, oxidation is going to mean either an increase in the number of carbon heteroatom bonds, where Z is an electronegative heteroatom, or it can also be a decrease in the number of carbon-hydrogen bonds. And often these things will go together. Sometimes you can have one without the other, sometimes you can't. Reduction is going to be the opposite of oxidation, so you'll be able to tell something is reduced because you will see a decrease in the number of carbon heteroatom bonds and or an increase in the number of carbon-hydrogen bonds. Yes? Hydrogenation is an example of reduction, yes. So common sort of functional groups that you learned back in chapter 3 about nomenclature, you can see now that their relative priorities were arranged according to how oxidized or reduced the carbons were. So, for example, you have carboxylic acids, esters, acid chlorides, amides that are at one oxidation state. Higher than that is CO2. That's fully oxidized carbon. Can you see that CO2 has more carbon heteroatom bonds than the acid does? You got sort of 4 here, you got 3 here. Next would be like the aldehydes or the ketones and a whole host of other things you will meet in 352. The acetal is an example of that, or the hydrate. Let's see, this is the acetal. Let's see, what else? The vicinal dihalide is sort of at this oxidation state. So that's 2 carbon heteroatom bonds. Then you've sort of got like the alcohol or the alkyl halide. At this sort of similar oxidation state, though there's not a carbon heteroatom bond, you can actually interconvert, and we now know how to do this, between olefins and alcohols and or acid chlorides using reactions that aren't oxidation reactions, so sort of at the same oxidation state. And then at the most sort of reduced oxidation state, you have the alkanes, hydrocarbons, and we use the reduced hydrocarbons in various settings, oil, we use it as gasoline, fossil fuels, and so on. All right, so moving up is oxidation. And then moving down is reduction. So you'll see that what we have done so far has mostly been at the 1 level of oxidation state. Interconverting, say, alcohols and acid chlorides. This was all chapters 7 and 8. Also converting an acid halide into an alkene was chapters 7 and 8. Alcohol chemistry was chapter 9. Then we had some chemistry with addition reactions to alkenes or olefins, and most of those reactions converted olefins back into stuff like this. So what you've seen so far has all been in this level, with one exception, and that is that the halogenation reaction, though we didn't talk about it at the time, that was an oxidation reaction. It involved, well, we don't need to go into the details. And one other thing I guess I will say is that you can put the alkyne at this higher sort of number 2 level of oxidation, because you can interconvert the vicinal dihalide into the alkyne via a simple E2 reaction. All right, so that's sort of the framework of oxidation state. We are going to learn some tools today for going from olefins and alkynes down 1 or 2 steps. Then next time we're going to learn some tools for going from an alcohol or an olefin up a couple of steps. We're not going to do all oxidation and reduction reactions. We're going to wait until 352 to talk about how to reduce acid chlorides or esters or so on to ketones or aldehydes. We'll wait on 352 to talk about ketones and aldehydes and some of these other groups. But this is sort of the map or the framework for everything we've been talking about. All right. Anything you want to ask about that? Yes? Why is the carbon triple bond on the level 2? Because you've decreased the number of carbon-hydrogen bonds. Yep.
So carbon-hydrogen bond is the most important.
Most important, or
like how we
well, so how you tell oxidation state? It's either of these, and sometimes they go together. So, for example, in going from an alcohol to an aldehyde, you pick up another oxygen-carbon bond and you lose a carbon-hydrogen bond. Sometimes those go together, but in other cases they're, and the olefin versus alkyne versus alkane is one of those where there aren't any heteroatoms, so you just have to watch the carbon-hydrogen bonds. Yeah?
So why would the alkene have, does the alkene have more electrons than the hydrocarbon?
Does the alkene have more electrons than the corresponding hydrocarbon, or less? Well, I suppose you can count them. C2H6, C2H4. I'm seeing 2 less electrons. So in some cases, you'll see with oxidation and reduction reactions, the way organic molecules react or work, going from here to here is an oxidation reaction, and you could think of it as the loss of 2 protons plus their electrons, or the loss of hydrogen, which you can understand to be either this, or this, or this. But yeah, you're losing electrons. And that sort of makes sense well, never mind. What I was going to say turned out to be cute, but not true. Maybe not even cute. All right, other questions? While we're at it, I mean, this isn't necessarily a thing having to do with this particular chapter, but I don't think we talked about it back when we were dealing with functional groups. I'll just say a little bit about hydrocarbons. Some of you have driven past the refineries sort of north of Salt Lake City and seen some of the towers and the fires that are going on there. And since you're in organic chemistry, it might be useful to just know sort of what's going on. So at an oil refinery, you've got crude oil, which is isolated from Earth, from dead things that used to be on Earth. And the idea is you're going to separate out various molecules. And we have lots of methods for separating out molecules in OChem, but one of the most useful in terms of oil refining is what's called distillation. And you learned in chapter 3 about non-covalent interactions how different length hydrocarbons have different boiling points. You can actually take advantage of that to separate out the components of crude oil into useful submixtures. So you take the crude oil and you put it in a very, very hot, what's called a heating tower. There are coils inside this heating tower that the oil flows through, and you're heating it somehow. There is the fire you're using to heat it. The heated mixture then comes out and goes to the distillation tower, and these are the tall sort of buildings that you see at a refinery. And it's hot down at the bottom, and as you get further up, it gets colder. Till by the time you get to the top, you're at basically room temperature, 20 to 25 degrees Celsius. And you have various stages of the cooling tower, or plates, that the hot crude oil components can condense on. So, for example, at about 350 degrees Celsius, you have motor oil condense, okay? So if you're using like not synthetic motor oil, but stuff that comes from crude oil, you're getting a mixture of hydrocarbons that condensed at 350 Celsius. If then another higher plate maybe is at 250 Celsius, this is like fuel oil, maybe diesel, not sure. If you've heard of kerosene, that's the stuff that condenses in the range of 175 to 275 Celsius. Again, that's going to be a mixture of hydrocarbons that all sort of condense at that temperature. Gasoline is at a little bit higher temperature. Again, gasoline's a mixture of hydrocarbons, mostly octane and isomers of octane. By the time you get to room temperature, what's left is stuff that is a gas at room temperature. We're thinking of the small alkane gases like methane and ethane, propane, and butane. And the problem with this, it's actually inconvenient to isolate these. And so what often happens, and if there's an excess of these, they just pipe that into a flame tower and light it on fire. I think most of the methane and propane and butane and such that we get is isolated perhaps from natural gas. I don't know whether or not they're able to isolate it here. In order to do so, they would have to get it pretty cold. Of course, you don't want to build up of any of these gases in a place where right next door you have something very hot, so they just prevent the explosion by burning it off all the time anyway. So the flaming towers you're seeing at an oil refinery are the volatile hydrocarbons that haven't been able to condense in the tower. Yes?
People have been making kerosene for hundreds of years. Do they still discover this way, like, for this?
Kerosene for hundreds of years? Don't know. Good question. I mean, you used to be able to get oil that you could burn from like whales, but that seemed kind of inhumane, so people don't do that anymore. Yeah?
There's different like octane ratings for gasoline. What does that look like?
Octane ratings for gasoline, good question. And I had that question last year. The answer is, wish I knew. Let's see how fast I can figure it out, shall we? You're about to see one of my superpowers here, and that superpower is, Grandma's lemon meringue pie. I did make that. It didn't turn out. The meringue sort of weeped all over the place, but you've got to get better at that. I sometimes get delusions of grandeur from watching the Great British Baking Show. My sponges are always stodgy. Okay, so octane rating is actually related to how much you can compress gasoline in a cylinder without it igniting. So it isn't, I think, directly related to the power output. And it seems like it's not, let's see, pro-ignition, knocking, all right, isooctane is reference standard. Yes, read the Wikipedia article. That is the answer to your question. I'm sorry, I don't know. Engine knocking used to be a problem, and that's no longer a problem, but sorry. My dad's a chemical engineer, and he knows all this stuff, but I don't. My apologies. Yeah?
I see them saying engine, but it had something to do with like the ice properties of it. Like the less it's a chain, the more it's like the.
Yeah, I mean, so it is related to isomers. You've got isooctane up on top here versus N-heptane. That's where the term octane rating comes from. This one has 100% on top. This one has 0%. Other than that, I don't know. How about I research it and try to explain it to you another time? Sounds good. You can hold me to it though, because I know professors sometimes say that and then hope you will forget. I mean, that's a time-honored strategy for children. We will talk about that later. All right? Okay, so reduction reactions. Let's talk about a reaction called hydrogenation. Of all of the reactions we've talked about so far this year, other than the ones that are going on inside of you, this is probably the one that you have most experience with, though perhaps inadvertently. This is addition of H2 hydrogen across a pi bond. So it's sort of weird because it sort of falls into the chapter 10 theme of adding to a pi bond, but it's a reduction reaction because you're going to increase the number of carbon-hydrogen bonds by 2. You're going to trade 1 carbon-carbon pi bond for 2 carbon-hydrogen sigma bonds. And so this is going to be exothermic. We got to do the math to determine that. Don't worry about that. So the reaction is to take an unsaturated hydrocarbon. We'll use ethane as our simple example. You use hydrogen gas, and you use a catalyst. The reaction's favorable, but you need a catalyst to get it going. And that catalyst is the transition metal palladium in its zero oxidation state. And when you use metal catalysts, often surface area can be a big deal. You want your molecule to be able to approach the catalyst and have lots of different reactive sites on the catalyst for the reaction to work. And so one of the ways they do that, instead of just throwing in a chunk of palladium metal, You can dramatically increase the amount of palladium surface that's available if you sort of grind the palladium up and you immobilize it on charcoal. And so we call this palladium on carbon. And you can buy this from various chemical companies. And what happens is you reduce the alkene or the olefin all the way to the alkane. Mechanistically, how does this happen? You're not going to really be held responsible for it. If you take 352, especially from Dr. Michaelis, you'll get a lot of experience with organometallic chemistry, and that will involve learning how metals influence and participate in reactions. Your text sort of summarizes what's going on here, and maybe I'll just try to do, we want large, there we go. So, why is this not working? All right, imagine a surface of palladium atoms. If you look at palladium's position on the periodic table, it's got a lot of d electrons that are available for reactions, and we don't need to necessarily worry about the nature of the reaction. As I said, you can learn more about it in 352. But what happens is the palladium, individual palladium atoms form bonds to hydrogen. Okay, so palladium first splits the hydrogen in two. For those of you playing along at home, you will notice that whereas hydrogen just came with 2 electrons, I've got 4 electrons involved here. 2 of those came from palladium, 2 of those came from hydrogen. It doesn't really matter. Then at that surface, the alkene can approach. And whoa, that's a really great sp3 hybridized carbon, isn't it? And then the metal can deliver on one side H minus with its electrons, and then on the other side the pi electrons attack the hydrogen, and you can imagine those electrons going back to the metal. And your product is this alkene where you've just attached those 2 groups to the carbons that were involved in the pi bond. So in this way, you can see how this is even if you're following and counting electrons, you can see how this is a reduction reaction, because 2 of the electrons that were here end up in one of the carbon hydrogen bonds. We see an increase in the number of carbon-hydrogen bonds, so that's a reduction reaction. Okay? That mechanism I'm not going to ask you about. It's somewhat unsatisfactory, but this reaction does work really well, and so people use it. There are a whole host of other catalysts that can do similar things. Some of them work better on different molecules, but for our purposes, we'll just use palladium on carbon. Let's see, what does this look like in the lab? A couple of different reaction setups. Let's see. Yes, that is how they do margarine. I'll just draw what it looks like in the lab. So you have a round bottom flask with a sort of stir bar at the bottom of it. You put the palladium on carbon catalyst in the flask. This is a sort of a dust powder that you can weigh out and inhale. That would be bad. Don't do that. You cover it with some organic solvent, whatever that is. We'll make it green even though it's not. You put your molecule that you want to reduce in there. So some molecule with a double bond. You put a stopper on the flask. Now, how are you going to get the hydrogen in? It's actually not as bad as you think. You fill a normal, regular sort of latex balloon with hydrogen gas. You attach that balloon to a syringe with a needle. You puncture the stopper with the needle so that there's a path for the hydrogen gas to get through, and that's usually enough to allow the reaction to start happening. And so it's really quite simple to do. The other nice thing is that it's very easy to, there are no byproducts, and it's very easy to filter out the catalyst, and so this is a clean reaction that you often don't need to do any purification step. Sometimes, I mean, if you're thinking about the engineering of the process, the maximum pressure of hydrogen you're going to get via the balloon method is 1 atmosphere of pressure. Sometimes to make the reaction go faster, you want to have the reaction pressurized. So there's actually reaction vessels that are called bombs that you put everything inside. You crank down on various bolts to keep everything together, and you can pressurize it to several atmospheres of hydrogen and then let it go. I've never done that before. Sounds scary. Any reaction says use this bomb doesn't sound like a great idea. All right, this reaction is what's used anytime you see a product where it says partially hydrogenated vegetable oil. They're talking about this reaction. We've talked before about how this step of the reaction is somewhat reversible, and so if you don't push the reaction to completion, there is the chance that you could take a cis double bond that's present in a natural fat or oil, and if you don't run the reaction to completion, you can isomerize that double bond to the trans stereochemistry. So if you've heard of trans fats, they are generated from incomplete hydrogenation of, they're byproducts of incomplete hydrogenation of oils. They're associated with some negative cardiovascular outcomes. Also, trans fat free, you should know, doesn't mean there's 0 grams of trans fat. It means there's less than a certain threshold. I think it's probably 0.5 gram. So in the eyes of the FDA, 500 milligrams of trans fat equals 0. So just be advised. Right. This is also, I think I brought in the 2 jars of peanut butter. One was sort of liquidy and weird. That was the one that had the cis double bonds in it. One was solid. That was the one that had been reduced to the alkane. The reason you would want to do this from a food industry standpoint is that these allylic carbons are reactive to oxidation reactions, radical oxidation reactions that you'll learn about in chapter 22. And if you oxidize that allylic carbon, you generate an oil that no longer tastes good and smells bad. So to avoid that and increase shelf life, it can be desirable to turn this oil into this longer chain hydrocarbon. Yeah?
What are the health impacts of that?
Health impacts of here, of going to from the unsaturated to the saturated. Saturated fats are also associated with negative cardiovascular outcomes and stuff, not a physician, so sorry, should know more about that. Wikipedia your exact question and probably you'll find the answer. Is that a verb now? Can you Wikipedia something? I think you can Google something still, but I don't know about that. Anyway, should learn more about that. What else? All right, what we'll do now is talk about what if you wanted to do this with an alkyne. One more thing. Because all of this happens on a surface, it is technically a syn addition. However, you can't tell for this simple alkene or olefin because there's no stereocenters. There's no way to tell that those 2 hydrogens were added to the same side of the alkene. If you wanted to demonstrate that, you could take a molecule like this and do catalytic hydrogenation, and you would observe that you get exclusively the cis product where the two hydrogens are on the same side of the original alkene. And that's just because it happens at the surface, and so the two hydrogens get added to the same face of the alkene. Now, if you started with an alkyne, what would happen? If you use most conventional palladium catalysts and you do the regular hydrogenation conditions, you can actually deliver two equivalents of hydrogen all the way to either of the carbons involved in both pi bonds. That's the first equivalent of hydrogen, here's the second. And so you can reduce the alkyne all the way to the alkane. Now, folks usually ask, well, can't I just measure out one equivalent of hydrogen and stop at the alkene? I suppose that's technically possible, but it's practically not fun. First of all, you can't weigh out hydrogen. It's lighter than air. Second, the way we do this, as I said in the lab, is we fill a balloon with hydrogen. So that's not really a precise measuring process. We have probably a vast excess of hydrogen relative to the molecule that's in solution. So we need better methods if we were wanting to take the alkyne and stop at the intermediate olefin stage. Presumably, the way this reaction would go is you deliver the first equivalent of hydrogen to get the alkene or olefin product, but then you would deliver the second equivalent of hydrogen to get to the alkane. All right? So, and the point is, if you use the regular palladium catalyst, you can't stop here. All right, so what are the strategies for doing that? For stopping at the olefin stage, we have two. The first is the use of a poisoned catalyst. That sounds way more exciting than it is. You basically add things to the catalyst to decrease its reactivity so that it can get from the alkyne to the olefin, but so that it's no good to take the olefin to the alkane. There are a lot of different things that work for this. If you read in your text, it will tell you what some of the things are. I'm just going to call them additives. So it's basically palladium on carbon plus some other stuff, including lead and I think some basic amines. But it slows down the reduction of alkenes to alkanes so that you can stop at the olefin or alkene stage. A lot of these catalysts are proprietary. One of the famous ones is called the Lindlar catalyst. Its actual structure, it's palladium on carbon with some additives, like I said. As to how it works, basically all of this is a mnemonic device. It's not really first principles. I'm just saying we through whatever method, tune down the reactivity of the catalyst so that you can stop. But the reduction still happens at a surface, and so you still get syn addition of hydrogen across one of the pi bonds of the alkyne. So if you take this alkyne that we've talked about and you use, again, hydrogen, similar setup as catalytic hydrogenation, only you're using the Lindlar catalyst, you can stop at the olefin, but you're going to get the cis olefin because it's a syn addition. All right, so that's option one. Option two, what if we wanted to get the trans olefin? This one's really kind of wild. You take your alkyne and you add to a cold reaction mixture. Your solvent here is liquid ammonia. Ammonia is a gas, at room temperature, so this has to be in a very cold reaction vessel. And then into that liquid ammonia, you drop a chunk of sodium metal. What do you guys know about chunks of sodium metal? You like to watch people throw them in lakes on YouTube, is that right? Okay. So you know that it's highly reactive and highly air sensitive, so you do have to be sort of careful with this. This reaction is sometimes called the dissolving metal reduction. Because when sodium liquid when sodium metal is put in liquid ammonia, the following reaction occurs. You take, and this 0 here indicates that this is sodium at the 0 oxidation state, not sodium plus. You get sodium and it expels an electron into the solution. Didn't really know that was possible. But in that process, you go from sodium metal to sodium ion, which can dissolve and is perfectly comfortable in ammonia. So it's basically like you've dissolved the metal. What does it mean to eject an electron into the solution? First, I don't know, but second, it probably is like this. You maybe have an electron surrounded by the partially positively charged hydrogens in ammonia. People sometimes call this a solvated electron. You basically have one electron shared across multiple atoms of, or rather multiple molecules of ammonia. So there's sort of a cage of ammonia molecules surrounding this hydrogen. And it turns out that this has a characteristic color. I bet you didn't know that an electron dissolved in ammonia is blue. So now I will use my Googling superpowers to show you what this looks like. Dissolving metal reduction. Illustrated glossary of organic chemistry. Let's see how illustrated it is. Ooh. Full screen is unavailable. Come on. So that's the reaction setup. There's the chunk of sodium metal. All of the apparatus here is all about condensing liquid ammonia, drops it in, and boom. Deep blue. That's kind of cool. Apparently, it's not air sensitive because the reaction is not on fire. Okay, so the effect of this reaction is to add electrons stepwise to the alkyne. So the reaction mechanism is in your text. We're not going to worry about that reaction mechanism, but think of it this way. Stepwise adding of one electron, then it picks up a proton. Then you add another electron, then it picks up another proton. That stepwise nature of the reduction causes you to stop, or rather causes you to get the trans alkene, because you're pausing at a place where you're not adding the two hydrogens at the same time, and you're pausing at a step where the hydrogen could either, at an intermediate where the hydrogen could either add from above or below, and it does so preferentially from below so that you can get the more stable trans alkene, sorry. So without mechanism, these are probably reactions that you're going to need to memorize. You'll need to, go ahead.
Will this give a racemate of trans instances, or will
It will only give you trans. Yep. Yeah, the dissolving metal reduction only gives you trans. So you're going to have to memorize those as tools, but once you know them as reagents and tools that you can use, you should be able to think about their stereochemical consequences strategically. So you don't want to do this, but I don't care. That's what I tell my primary children. Never ask primary children, should we sing song X? Because the answer will always be no, and then I have to say, I don't care what you think, I'm in charge. Which they think is funny, but anyway, go ahead.
So, where does the hydrogen come from?
The hydrogen comes from, NH3. Some of the intermediates have negatively charged carbons, and so those are strong enough bases to pull off a proton from NH2. One of the byproducts we're not showing here is NH2 minus. By the way, students really struggle to distinguish this from something you saw previously where you can take a vicinal dihalide and while using sodium plus NH2 minus, do the tandem E2 reactions to get the alkyne. People mix that up all the time. Don't let it happen to you. Right, so with all of this in mind, I can now start to ask you questions that require you to think through stereochemical consequences of reactions. For example, what if I wanted to end up with, vicinal dihalide A versus vicinal dihalide B, and I gotta start, let's make this really simple. I don't want R groups, let's just use methyls. Okay, what am I going to do? And hint, you're going to need more than one step. Other hint, you better be able to get the stereochemistry right. That's the whole point of this question. Don't ask for partial credit if you can't get the stereochemistry right. That seemed kind of harsh, I'm sorry. But I still mean it. Okay, so think this vicinal dihalide. What is the immediate precursor? What do we do? What is the starting material that gives you, and the reagent that gives you a vicinal dihalide? It's a what? Al something or other? Alkene. Okay, fine. But which one is it? Is it this one or this one? It is this one. How can you tell? You can tell because I just so happen to draw the product in an orientation where the BRs are on opposite sides. You know that addition of Br2 to an alkene is an anti-addition. So it stands to reason that if you draw the molecule in such a way that the BRs are anti to each other, that will tell you what the stereochemistry of the alkene must have been. Do you see how when these two bromos are trans to each other, the methyls are also are anti to each other, the methyls are also anti to each other? And the only way for that to be true here is if it were true in the alkene or olefin starting material. I'm going to just say olefin because I screw up alkane and alkene, and in any case saying alkene seems a little nasally, so don't want to, whatever. Okay, so what reaction conditions can I use to convert the alkyne into the trans olefin? That dissolving sodium metal thing, good. That dissolving sodium metal thing will not be an option on the exam, so you'll have to know what those reagents are. Okay, does that work? Yes, this gives you the trans olefin, and then you can do anti-addition to give you this product. What about B? First thing that's going to deceive you about B is you're going to look at that and say, wait, Wait. Syn addition of Br across a double bond? I don't know of a reaction that takes the trans olefin and does syn addition of Br2. Yeah.
Did you use that hydrogenation reaction to get it to a single bond and rotate the carbon one?
So, sorry, could you do, yeah, I think, are you saying that I could rotate here and see that there is,
Yes.
okay. Right, so beware the concealed stereochemistry issue where actually it is an anti-addition. I've just drawn it in such a way that it no longer looks like that. And so you have to be thinking in your brain, okay, how do I rearrange this molecule so that the BRs look anti to each other so I can tell what the olefin starting material would have been? What is the correct olefin starting material then? Yep, it is the cis olefin. So you can use Br2. How do I get the cis olefin? Scroll up, that you haven't memorized it yet, you need to. The Lindlar catalyst does syn addition of H2 across the alkyne. Okay? Gonna get worse. Because this is not the only way I can test your knowledge of stereochemical consequences of reactions. We're going to actually learn how to make epoxides, and then all of that horrible stuff we did before with epoxides is going to come back and be combined with this alkene stereochemistry business. But we're not quite there yet. Questions you want to ask about this? I mean, I'm giving away all my secrets. I can guarantee you there is a problem like this on the exam. There is a problem like this on the exam. It might not involve vicinal dihalides, it might involve epoxide stuff, but if you get these two mixed up, you're going to lose some points, and I will not give you partial credit because I've warned you all, right? Okay. I don't know, I told you so is never comforting after the fact. I'm hoping that threatening you that I will tell you I told you so might motivate you to master some of this stuff. All right, questions? Yeah. The Lindlar catalyst again, yeah. This is just as to what it is and what its components are, it's palladium on carbon plus various additives. It gives you like regular hydrogenation, syn addition of H2 across a pi bond, and that's why you get the cis olefin. The reason you stop at the olefin instead of going on to the alkane is that these additives, slow down the catalyst. All right. We'll see you next time.